Okay, so today we'll be working through Proposition 11. Proposition 11 is the first of three propositions which will deal with the conic sections directly and sort of define the way that they curve for every point along the curve. So these are probably the three most important propositions in Book 1 or in the entirety of conics. So I'm going to take this one slow and try to, do it right. So I thought one of the things that I would do is go through the enunciation, because starting in this proposition, I think the enunciations get pretty difficult to read, and although there's a trick you can always do, you can skip to the part of the proposition where it says I say. That's always going to be what the proposition is trying to prove in simple terms or in terms of the actual labeled lines. I think it's good to understand the generalization and to be able to read the enunciation in terms of what parts of it relate to what, and because I think it's hard, I think I'm just going to go through this one. So let's do that. If a cone is cut by a plane through the axis, if you hear the word plane through the axis, it's probably always going to be in the axial triangle. I guess we'll label it. And also cut by another plane cutting the base of the cone in a straight line perpendicular to the base of the axial triangle. So there's going to be another plane, and it's going to cut this plane so that this is perpendicular. And if further, the diameter of the section is parallel to one side of the axial triangle. So let's say we construct this section so that this is the diameter and that it's parallel to the side AB. Let's label our points real quick. Maybe F. And if any straight line is drawn from the section of the cone to its diameter, such that this straight line is parallel to the common section of the cutting plane and the cone's base. So the common section of the cutting plane and the cone's base would be DE here. So we're trying to, first off, let's draw the section. So we're trying to draw a straight line which is from the section to the diameter and which is parallel to the common section of the base of the cone and the section, which would be DE. So we've constructed this line here, parallel to this line here. Okay, so we're here now. Then this straight line to the diameter, the one we just did, I guess I'll label it KL, will equal in square the rectangle contained by, so what that's saying is that the square on KL will equal a rectangle contained by, from the straight line from the section's vertex to where the straight line to the diameter cuts it off. That would be FL. And B, another straight line. It doesn't say which one, so let's construct it. I only know that I'm supposed to construct it in retrospect, but I'll just save you time. Which has the same ratio to, so now this is starting another clause. So say FH has the same ratio to the straight line between the angle of the cone and the vertex of the section. This is the vertex of the section. This is the angle of the cone. So that would be this line, AF. As the square on the base of the axial triangle, that would be BC, has to the rectangle contained by I forgot to put square here. The two remaining sides of the triangle. So that would be AB, AC. And let such a section be called a parabola. So let's go back and say what the hell this means. So what we're trying to prove is this. The square on KL is equal to the rectangle on FL, FH. When we've constructed FH such that as FH is to AF, the square on BC is just the square on ABAC. This line FH is going to be pretty important going forward, and we're going to call this the upright side. Sometimes we're going to call this the parameter, and I personally like to call it the kickstand, because it's like kicked out from the section. I don't know. I just think that's a cute name that helps me remember which part of this is which thing, because upright side, you know, they could all be upright, right? But let's think about this. If this were to always be true, then if you picked any point K, you would have some idea of a relationship between this side and this side, because KL would be this square, and then FL would be here, and FH is always going to be the same line, so anything multiplied by the same thing, it doesn't matter, right? So what we're really trying to do with this proposition isn't just prove some bizarre equality. We're trying to keep track of the ratios between these two types of lines within the section. And if you think of a parabola, you're normally used to the Descartes version of this. You know, you might have some line that looks like this. Here's x, here's y equals x squared, or some manipulation of that, right? So what you're doing when you say y equals x squared is, for every point, you know that its y coordinate has some stable relationship to its x coordinate. So these lines that I've highlighted here, you can think of these as sort of older versions of that, right? You're still trying to find a way to preserve this relationship such that you could pick any point along this curve and you'd have the same type of relationship, or you'd know based on like one side what the length of the other side would be. This is a website called whistleralley.com. As far as I know, it's just some guy named, what was his name? Some guy named Paul Kunkel, who just put together a bunch of diagrams for the Apollonius proofs in his spare time. And he has a whole page of these sort of like diagram demonstrations of how different values relate to different lengths of lines. And I think this one is relevant to this proposition. So this is a parabola, and you've got the lengths AC and CP over here, and then you've got the square on the side of PC divided by the lengths of the cutoff diameter is equal to 104. So what do you think is going to happen if I move the point P around? Well, these length numbers up here are going to change, but this ratio is not going to change. So that's what I was trying to say earlier about we're trying to sort of have this curve be something that's defined and something that we can know about at each point P. And this is kind of a spoiler for later props, but you might be able to move A and then have a different diameter. So now you have, instead of whatever it was over here, 104 or something, you might have the ratio between them come out to a different value, but if you keep this consistent and you move P around, you notice that these two values change, this one does not. So relative to whatever diameter you're talking about, this ratio will not change. Okay, welcome to the proof part of the proof. The first thing we're going to do is we're going to draw a line through L, which is parallel to BC. Okay, so we're going to label this MN. And because MN is parallel to BC and KL is parallel to DG, we know that the points M, K, and N are all lying in a plane which is parallel to the plane BDC of the base, so they would cut off a circle. And in a circle, if you have a line dropped perpendicular to the diameter, we know this is perpendicular because MN is parallel to BC and DG was constructed perpendicular to BC. This is parallel to DG. But if you have a line drop perpendicular to the diameter of a circle, then the rectangle on the cutoff parts of the diameter, which will be ML and LN, are going to be equal to the square on the part cutting it off, which will in this case be KL. So that's one thing we're going to start out with. The other thing we're going to start out with is how we constructed FH. If you remember, the enunciation told us that FH is to FA as the square on the base of the axial triangle is to the rectangle made from the other sides of the axial triangle. So that's CA, BA. Okay, so those are the two things we're going to start out with. Now let's write out BC is to CABA as the ratio BC to CA is compounded with the ratio BC BA. Now I'm going to explain what that means. So the word compound here, just think of that as being a multiplication symbol. So if you're ever confused by ratios, you can always write them out as if every one of these colons is a division symbol. Anything like a rectangle or a square could be written out like BC times BC. And every two colons could be written out by like an equal sign. Compound means multiply. So that's a quick visual aid as to what compounded ratios are. But if you want to check the Euclid, it is, I believe, Euclid 623. But yeah, that's just an explanation going forward of what compounded ratios are, how they work. But basically going forward, if we ever have something on one side of a ratio which is a square or a rectangle, we can think of this and sort of FOIL it. So BC times CA, one side, BC times BA, another side. And we could do this in reverse. If we have something like this, we could say that this is in the same ratio with, and then we could sort of FOIL BC square is to CABA as a rectangle. But you'll see me doing that as we go forward. So for right now we have the square on BC is to CABA as the ratio BC to CA is compounded with the ratio BC to BA. So now those two terms are the same. So let's rewrite and let's do FH is to FA as, these two terms are the same, so we'll substitute BC CA compounded with BC BA. And now we're going to try to substitute for these little parts. So let's look at where BC is and CA is. So the ratio BCCA is the same as the ratio MNNA because the triangle ANM is sort of constructed with this line parallel to this line. So they're similar. So BCCA, MNNA. And this triangle, FLM, this side are shared with AMN, and FL is parallel to AN. So as MN is to NA, ML is to LF. So I'll write ML, LF. Now let's think about BCBA. BCBA. So what could we substitute with this? Just write it out first. Well, with this triangle, we could substitute it with MNMA. So let's do that. With this little triangle, we could do LMMF. But most importantly, from Euclid 6.2, we know that if we have a triangle and then we have a similar triangle within it, this parallel side will cut off sides that are proportional, meaning that as MN is to MA, LN is to FA. We have MN and we have MA. So it has the same ratio to LN and FA. Okay, so let's take this term, let's copy it down here. And then let's look at BCCA. BCCA has the same ratio to MLLF. So let's substitute this part with MLLF. Let's keep the compounded. And then BCBA right here can be substituted with LNFA. So just as I've explained before what compounded ratios are and how you can take them from figures, let's now do the reverse and put this back into figures by sort of foiling it out. So I'll do FH to FA is as the rectangle ML LN, ML LN is to the rectangle LF FA. Oh. So this is where we are right now. Now we're going to just look at FHFA. And we are going to multiply, or just think about it as multiplying, each term on the left with one common line. And the common line is going to be FL. So FH times FL is the rectangle FH FL. FL times FA is the rectangle FL FA. So we know that FH is to FA as FH FL is to FL FA because we've just multiplied both by the common term FL. And that's from Euclid 6.1. So now we're going to substitute FH FA on this side with what's on this side. So we have ML LN is to LF FA as FH FL is to FL FA. Now FL FA and FL FA is repeated twice. So if two things have the same ratio to the same thing, then we know that they're equal. That's from Euclid 5.11. So that means that MLLN must be equal to FHFL. So we've got MLLN equals FHFL. And where's MLLN? Well, all the way back up here, showed that MLLN was equal to KL. So that means KL is equal to the rectangle FHFL. And that's what I like to call the kickstand, or the upright side, and the diameter cut off by the ordinate. The rectangle made up of those is equal to the square on the ordinate. And that's what it was required to prove. So QED. Thanks for watching.